Hey guys, welcome again. Now, in today's presentation, we are going to discuss about a very important topic which has a greater impact on our lives, on our society, on our culture, or on total humanity as a whole. That is quantum computing. So, without wasting any time, let's start. But first, let me introduce myself, right? I'm a student. My name is Sai Krishna actually, and I'm a student currently pursuing the data science bachelor's degree at IR. So, what are the objectives of today's presentation? First, we will introduce what is quantum computing or quantum mechanics exactly, then the history of it, what are the possible applications, and what are the challenges in order to make it into a reality. Introduction. Quantum computing holds the promise to solve some of our planet's biggest challenges in the areas of environment, agriculture, health, energy, climate, material science, and others we haven't encountered yet. For some of these problems, classical computing is increasingly challenged as the size of the system grows. When designed to scale, quantum systems will presumably have some capabilities that exceed our most powerful supercomputers. As the global community of quantum researchers, scientists, engineers, and business leaders continue to collaborate to advance the quantum ecosystem, we expect to see quantum impact accelerate across every industry. Just a bits are the fundamental units of information in classical computing. Qubits, quantum bits, are the fundamental units of information in quantum computing. While a bit or a binary digit can have a value either 0 or 1, a qubit can have a value that is either 0, 1, or a quantum superposition of 0 and 1. Efforts towards building a physical quantum computer focuses on technologies such as transmons, ion traps, and topological quantum computers which aim to create high-quality qubits. These qubits may be designed differently depending on the full quantum computer's computing model as to whether quantum logic gates, quantum annealing, or adiabatic quantum computation are employed. These are currently a number of significant obstacles to constructing useful quantum computers. It is particularly difficult to maintain qubits, quantum states, as they suffer from quantum decoherence and state fidelity. Quantum computers therefore require error correction. Any computational problem that can be solved by a classical computer can also be solved by a quantum computer. Conversely, any problem that can be solved by a quantum computer, that's it. Now, any computational problem that can be solved by a classical computer, yeah, we have gone through this again. Now, so yeah, we need to focus on quantum complexity theory. In other words, quantum computers obey the church Turing thesis. This means that while quantum computers provide no additional advantages over classical computers in terms of computability, quantum algorithms for certain problems have significantly lower time complexities than corresponding known classical algorithms. Notably, quantum computers are believed to be able to quickly solve certain problems that no classical computer could solve in any feasible amount of time, a feat known as quantum supremacy, the study of the computational complexity of problem. Now let's talk about history. Despite ongoing experimental progress since the late 1990s, most researchers believe that fault-tolerant quantum computing still a rather distant dream. In recent years, investment in quantum computing research has increased in the public and private sectors. On 23rd October 2019, Google AI, in partnership with the US National Aeronautics and Space Administration, commonly and popularly known as NASA, claimed to have performed a quantum computation that was infeasible on any classical computer. But whether this claim was or is still valid is a topic of active research. It is December 2021, McKinsey and Company analysis states that investment dollars are pouring in and quantum computing startups are proliferating. They go on to note that while quantum computing promises to help business solve problems that are beyond the reach and speed of conventional high performance computers, use cases are largely experimental and hypothetical at this early stage. So let's talk about some applications and start with quantum algorithms. Quantum computing began in 1980 when physicist Paul Benioff proposed a quantum mechanical model of Turing machine. Richard Feynman and Yuri Manin later suggested that a quantum computer had the potential to stimulate things a classical computer could not feasibly do. In 1986, Feynman introduced an early version of quantum circuit notation. In 1994, Peter Shor developed a quantum algorithm for finding the prime factors of an integer with the potential to decrypt RSA encrypted communications, essentially hacking man. Quantum hacking in 1990s. Great. In 1998, Isaac Chuhang, sorry for the pronunciation, Neil Gershenfeld, and Mark Cubanik created the first two-qubit quantum computer that could perform computations. Despite ongoing experimental progress since 1990s, most researchers believe that fault-tolerant quantum computing still a rather distant dream. In recent years, investment in quantum computing research has increased in the public and private sectors. On 23rd October 2019, as I already said, Google and NASA have committed an agreement to develop and research on quantum computing. And this is that. Now let's talk about cryptography. A notable application of quantum computation is for attacks on cryptographic systems that are currently in use. Integer factorization, which underpins the security of public key cryptographic systems, is believed to be computationally infeasible with an ordinary computer for large integers if they are the product of few prime numbers, product of 300-digit primes. By comparison, a quantum computer could effectively solve this problem using Shor's algorithm to find its factors. This ability would allow a quantum computer to break many of the cryptographic systems in use today, in the sense that there would be a polynomial time in the number of digits of the integer algorithm for solving the problem. In particular, most of the popular public key ciphers are based on the difficulty of factoring integers or the discrete logarithm problem, both of which can be solved by Shor's algorithm. In particular, the RSA, Diffie-Hellman and elliptic curve Diffie-Hellman algorithms could be broken. Essentially, when quantum computing becomes mainstream, hacking would be very easy. That even a 5-year-old can do things. Crazy, right? These are used to protect secure web pages. So the before mentioned algorithms or the cipher keys are used to secure web pages, encrypted emails, and many other types of data. Breaking these would have significant ramifications for electronic privacy and security. Identifying cryptographic systems that may be secure against quantum algorithms is an actively researched topic in the field of post-quantum cryptography. Some public key algorithms are based on problems other than integer factorization and discrete logarithm problems to which Shor's algorithm applies, like McEllis crypto system based on a problem in coding theory. Lattice-based crypto systems are also not known to be broken by quantum computers, and finding a polynomial time algorithm for solving the dihedral hidden subgroup problem, which would break many lattice-based crypto systems, is a well-studied open problem. It has been proven that applying Grover's algorithm to break a symmetric algorithm by brute force requires time equal to roughly 2n by 2 invocations of the underlying cryptographic algorithm, compared with roughly 2n in the classical case, meaning that asymmetric key lengths are effectively halved. AES 256 would have the same security against an attack using Grover's algorithm than that AES 128 has against classical brute force research. Quantum cryptography could potentially fulfill some of the functions of public key cryptography. Quantum-based cryptographic systems could therefore be more secure than traditional systems against quantum hacking. Now, search problems. The most well-known example of a problem that allows for a polynomial quantum speedup in unstructured search. Problem that can be effectively addressed with Grover's algorithm have the following properties. There is no searchable structure in the collection of possible answers. The number of possible answers to check is the same as the number of inputs to the algorithm. There exists a Boolean function that evaluates each input and determines whether it is the correct answer. For problems with all these properties, the running time of Grover's algorithm on quantum computers scale as the square root of the number of inputs or elements in the database as opposed to the linear scaling of classical algorithm. A general class of problems to which Grover's algorithm can be applied is Boolean satisfiability problem, where the database through which the algorithm iterates is that of all possible answers. An example and possible application of this is a password cracker that attempts to guess a password. Breaking symmetric ciphers with this algorithm is of interest of government agencies. Now, simulations of quantum systems. Since chemistry and nanotechnology rely on understanding quantum systems and such systems are impossible to simulate in an efficient manner, classically many. I believe quantum simulation will be one of the most important applications of quantum computing. Quantum simulation could also be used to stimulate the behavior of atoms and particles at unusual conditions such as deep reactions inside a collider. Quantum simulations might be used to predict future paths of particles and protons under superposition in a double-slit experiment. About 2% of the annual global energy output is used for nitrogen fixation to produce ammonia for the HAPER process in the agriculture fertilizer industry, while naturally occurring organisms also produce ammonia. Quantum simulations might be used to understand this process and increase the production by improving efficiency. Quantum annealing. Quantum annealing or adiabatic quantum computation relies on the adiabatic theorem to undertake calculations. A system is placed in the ground state for a simple Hamiltonian which is slowly evolved to a more complicated Hamiltonian whose ground state represents the solution to the problem in question. The adiabatic theorem states that if the evolution is slow enough, the system will stay in its ground state at all times through the process. So what? Then machine learning, of course. Of course, since quantum computers can produce outputs that classical computers cannot produce efficiently, that's the important word. And since quantum computation is fundamentally linear algebraic, some express hope in developing quantum algorithms that can speed up machine learning tasks. For example, the quantum algorithm for a linear system of equations or HHL algorithm, named after its discoverers Harrow, Hasidim, and Lloyd, is believed to provide speed up over classical counterparts. Some research groups have recently explored the use of quantum annealing hardware for training Boltzmann machines and deep neural networks. Now, what will be the developmental challenges? Primarily, there are a number of technical challenges in building a large-scale quantum computer. Physicist David DiVincenzo has listed these requirements for a practical quantum computer. Physically scalable to increase the number of qubits. Qubits that can be initialized to arbitrary values. Quantum gates that are faster than the decoherence time universal gate set. Qubits that can be read easily. Sourcing parts of quantum computers is also very difficult. Many quantum computers, like those constructed by Google and IBM, need helium-3, a nuclear research byproduct, and specially superconducting cables made only by the Japanese company Coax Co. The control and multi-qubit system requires the generation and coordination of a large number of electrical signals with tight and deterministic timing resolution. This has led to the development of quantum controllers which enable interfacing with the qubits. Scaling these systems to support a growing number of qubits is an additional challenge. Now, what will be the summary? Quantum mechanics is the base of all quantum mechanics. Yeah, both are proportional. Now, quantum computing is totally based on weirdness of qubits, right? How weirdly they interact. Now, there are many potential applications and developmental challenges in the process of mainstreaming quantum computers. And that's the summary. Thank you for listening, guys. I hope you have learned much about quantum computing in the context of quantum mechanics and how it has the potential in various fields. So, I'll come with another presentation. Till then, have a good one.